everyone. So today we are going to discuss about the last configuration of the MOSFET. It is common drain amplifier. It is also known as source follower. I will tell you the why the name came source follower for common drain amplifier. So the three configurations we have seen is first configuration is common source, common gate, and common drain. Out of which we have studied common source with and without source resistances, and we have seen the various characterizing parameters like what is the input resistance, what is the open circuit voltage gain, and what is output resistance and the overall voltage gain. Okay, so today we are going to see the last configuration of the MOSFET, common drain amplifier configuration or source follower configuration. So what is this common drain or source follower? This circuit is able to provide a very high input resistance and very low output resistance, and is used to act as a buffer amplifier. Whenever we say amplifier, the very first thing come to our mind is amplifier used for the amplification purpose. But here, common drain amplifier, it will be acting as a buffer amplifier. What do you mean by buffer amplifier? Whatever the input we give, same thing output we are going to get. That is, output and the input, there is no, or at the output side there is no amplification. The voltage gain will be 1. Voltage gain will be 1. So this find the common drain amplifier, it finds application in the in wherever we want high input resistance and low output resistance. At that time we are going to make use of this common drain amplifier. Their gain doesn't matters. Okay, so what is the need for this voltage buffers? So why simply we need to use the op-amp to which acts as a voltage buffer. Buffer means whatever the input we give, output we are going to get the same. Right. So what is the use of this voltage buffer? That scenario, it is being shown over here. So here they have told very first point, it finds application in the design of both small signal amplifiers as well as amplifiers that are required to handle large signals and deliver substantial amount of signal power to the load. Means this particular common drain amplifier, which will be having the high input resistance or the impedance and low output resistance or the impedance. So what is the need for this voltage buffer? In the first picture you can see here the signal, it is being given, and our signal, it is the internal resistance of the signal, and at the output side we have got the load resistance 1 kilo. So how this input and the output is connected, that is shown in the, suppose if we connect the signal directly to the load, what is going to happen? See, the 1 volt we have provided, very less amount of output we will be getting. That is voltage across the load. If we calculate, we will be getting the, that is voltage divider rule. V naught is equals to RL divided by R signal divided by RL plus R signal into V signal. So if you substitute all this value, you will be getting the output voltage as 1 millivolt. You see the input and you see the output. When you directly connect the source to the load, there will be attenuation in this signal. So that is why, in order to avoid that, we are making use of the buffer. Okay, so when you use this, what happens? The input resistance of this will be very high and output resistance will be very low. So whatever you give here, same thing you will be getting, because the output gain, it is nothing but 1. Whatever you give here, same thing you will be getting here. Because of this load resistance, there will be some amount of drop will be there. Some amount of, because 90% of the signal voltage will present at the output of the amplifier. So we can expect not exactly 1 volt, we can expect 0.1 volt lesser than that, that is 0.9 volt. So this is why we require voltage buffer. If we connect the directly, if we connect source directly to the load, there will be a attenuation in the signal. Okay, that is why, in order to avoid that, we'll be making use of voltage buffer. Voltage buffer, which will be having gain is equals to 1. So whatever you give here, same thing it will be observed at the output of the amplifier. So a signal source delivering a signal of reasonable strength of 1 volt, 1 volt is given, with an internal resistance of 1 mega, is to be connected to the 1 kilo ohm load. Connecting the source to the load directly, which is shown in the figure B, would result in a severe attenuation of the signal. So the signal appearing across the load will be only 1 divided by 1000 plus 1. So that is signal appearing across the load. That is what I told, voltage divider. Voltage divider, this much amount of the input signal or above 1 milli or about 1 millivolt we are going to get at the output across the load. Across the load, this much we are going to get. Means there is an attenuation in the signal from 1 volt to 1 millivolt. So the alternative course of action which is suggested in the figure C, that is the use of buffer amplifier. Here we have interposed an amplifier between the source and the load. So amplifier, however, is unlike the amplifiers we have been studying this chapter thus far. It has a voltage gain of only unity, means AV, overall voltage gain, which is equals to 1. In the sense, here we are not using amplifier for the amplification purpose, only to provide the output resistance low and input resistance high. We'll be making use of this amplifier. So this is because our signal is already of sufficient strength. We do not need to increase its amplitude. Okay, that is why amplification is not done over here. Only from the loading point of view or inputting from point of view, we'll be using this kind of amplifiers. Okay, so note, however, that our amplifier has a very large input resistance. Thus almost all of the input signal applied, V signal, will appear at the input of the amplifier. Since the amplifier has a low output resistance, that is of 100 ohm, so the 90% of the signal, that is 0.9 volt, will appear at the output. Obviously a very significant improvement over the situation without the amplifier. This is why we require the voltage buffer from source, in between source and the load. And here comes the actual circuit diagram of common drain amplifier or source follower. So very first figure shows it is a MOSFET, including the MOSFET. What is the input signal given? It is a signal, V signal, with an internal resistance of R signal. Okay, and then at the output side, see the source, we are taking the output, so the load resistor is connected to the source terminal and the drain is grounded. And R in depicts it is an internal resistance, R out is a output resistance, V naught across the load resistance, and VI we are giving at the between the gate and the source terminal. Okay, so very first figure, which is a general figure. The second figure, which shows is the equivalent circuit of the source follower obtained by replacing the MOSFET with its T model. T model already I had explained in the last session, that is in the common source amplifier with the source signal source. So here the MOSFET, it has been replaced. The gate terminal. See, this is the gate terminal that has been directly shorted to this particular junction, and in this junction you can see one current is entering, dependent current, and same current it will flow because Ig is 0. So this current and this current, Id and Is, it is same, and here your current, it has been replaced by the resistance with a value of 1 over Gm. We know how this 1 over Gm we have got. I explained in the last session. Okay, so here the current, it has been replaced by the resistance, source resistance RL, 1 over Gm. Okay, and then to the source terminal RL is connected, same thing over here. And here in the last case, that is common source amplifier, we have not considered R0. For the analysis purpose we have omitted this R0, but in this particular picture they have shown the R0. See where R0 is connected, that is in between the output terminals. Output terminal is nothing but the source and the drain. So here across it R0 is connected. Understood? Now Ig is 0, this you have to show, and the same current here flows and RL is connected here, and across the RL we are going to obtain the output. This is the T model. T model we are going to obtain from the pi model. Okay, so this is the equivalent, simplified equivalent model, that is same picture it is, but without R0. So if we include the R0, the analysis will be quite complex. That is why R0 will be omitted for the analysis purpose. So without R0, the picture it has been given over here, and R0 output resistance, see the input resistance is shown here, it is infinite, and the output resistance, it is 1 by Gm, because output resistance will be calculated by considering the V signal as 0. If Vi as 0, if Vi is 0 means what is going to happen, this will be 0, right? So you will be getting only 1 over Gm, so R naught will be equals to 1 over Gm. This is by output resistance. So let us now know about various characteristic parameters of the source follower. So what are these characteristic parameters? Of course, in the last session, that is in the source common source amplifier, we have seen the characterizing parameters of the amplifiers, like what is the input resistance, what is the open circuit voltage gain, what is the output resistance, what is the overall voltage gain. Similar to that, in the common drain or source follower, we are going to see the characterizing parameters. So the source follower is fed with the signal generator, that is, it is fed with the input signal of V signal with the internal resistance of R signal, and has loaded a load resistance RL connected between the source terminal and the ground. RL is connected between the source terminal and the ground, and it is being provided with the signal generator of V signal with an internal resistance of R signal. Next, we shall assume that includes both actual load and any other resistance that may be present between the source terminal and the ground. For example, biasing, for the biasing purpose will be making use of external DC supply. So normally the actual load resistance RL would be much lower in value than such other resistances, and thus it would be dominate. So since the MOSFET has a resistance connected in its source terminal, it is most convenient to use the T model. That is why T model it has been chosen. Otherwise, any other models can be used. Here, because the source terminal, there is a resistance, load resistance. That is why T model it has been considered in the common drain. So note that we have included simply because it is very easy to do so. However, since R0 in effect appears in parallel with RL, that is, they are talking about the output resistance of the MOSFET, and since in discrete circuit R0 is very much greater than RL, we neglect this R0 and obtain the simplified equivalent circuit in the same as the previous figure. So this R0, whichever it is connected between the drain and the source terminal, it has been omitted because R0 is very much greater than RL. That is why R0 is omitted. So we can do the following as a inspection, that is various characterizing parameters we are going to obtain here onwards. The very first characterizing parameter is the input resistance, that we know it is infinite, very high input resistance, so it is considered as infinite. Next, you obtain the AV from the voltage divider formed by 1 over Gm and RL. See, AV is nothing but V0 by Vi. AV is nothing but V0 by Vi. So here, see, Vi is nothing but, which includes Vi is the voltage across 1 over Gm and RL, and output is nothing but across RL we are going to get the output. So what is this gain? Gain is nothing but V0 divided by Vi. So how we are going to obtain V0? V0 is nothing but voltage across RL. It is a voltage divider rule between these two resistances. So if I want the voltage across RL, it is nothing but RL divided by RL plus 1 over Gm into Vi. This is the voltage it has been divided between these two, right? So it is like V0 by Vi, RL divided by RL plus 1 over Gm. And setting RL to infinity, we obtain the voltage gain as 1. So the load resistance will be very much high, then only we will be getting the voltage gain, open circuit voltage gain as 1. That is what the actual thing here, that is common drain voltage gain is 1. Voltage gain is 1 means we need to make RL as infinite. By setting RL as infinite, what it will become, this particular thing will be very much lesser. So RL by, it will be like nearly approximately RL by RL, because this is very much lesser. This value will be very much lesser, 1 over GM. So RL by RL, infinite by infinite is nothing but 1. So the output resistance, let us calculate next. The output resistance R0 is found by setting Vi is equals to 0. As I told earlier, your output resistance will be calculated by setting the input signal as 0. So by grounding the gate terminal, we are going to calculate R0. So now looking back into the output terminal, that is excluding RL, load resistance we need not include to calculate R0. So simply we will be getting 1 over GM. R0 will be equals to 1 over GM. You can see in the figure, excluding RL, if this is connected to the ground, we will be getting only 1 over GM. We won't be getting any other terms over here. It is just 1 over GM excluding RL. So R0 will be exactly equals to 1 over GM. Okay. Next, the unity open circuit voltage gain together with the R0 output resistance can be used to find the gain, voltage gain, overall voltage gain when a load resistance is connected. When RL is connected, what is the overall voltage gain? So the result is simply the expression in equation, this one. Finally, because of the infinite input resistance, your Vi will be equals to same as that of the signal we applied, input signal we applied, and the overall voltage gain, that is GB, which is nothing but same as open circuit voltage gain. Okay, so RL divided by RL plus 1 over GM. So since by making RL as infinite, this will be very much lower. Infinite by infinite means we will be getting the overall voltage gain as low. Thus GB will be lower than unity. However, because 1 over GM is usually very low, so the voltage gain can be close to unity or it should be lesser than unity. So the unity open circuit voltage gain in equation 5.90, that is this one, unity voltage gain, open circuit voltage gain, indicates that voltage at the source terminal will follow that at the output. So will follow that at the output, hence the name source follower. That is why it is known as the source follower. The voltage, see, the unity open circuit voltage gain, that is AV naught is equals to 1, indicates that voltage at the source terminal will follow that at the input. That is source, and source terminal is the output terminal. So this voltage, which will be same as that of the, see, if AV is 1 means V naught is equals to V in. V in is nothing but the gate terminal we are applying, and the voltage at the source terminal is the output voltage. So Vs is equals to Vg. That is why it is the name given source follower. So in conclusion, we can say that the source follower features a very high input resistance. Ideally, it is infinite, and relatively low output resistance, and an open circuit voltage gain that is nearly unity. Ideally, it is unity. Thus, the source follower is ideally suited for implementing the unity gain voltage. That is, it will be acting as a buffer amplifier. So the source follower is also used as the output, that is last stage in a multi-stage amplifier, where its function is to equip all overall amplifier with a low output resistance, thus enabling it to supply relatively large load currents without the loss of the gain. That is, with little reduction in the output signal level. Very much little reduction in the output signal level. So voltage gain will be 1. So let us summarize all the amplifier type characteristic parameters. So the first amplifier type, that is a common source without the signal resistance, source resistance RS. So various characterizing parameters over here, it is, one is R in, input resistance. Next is the open circuit voltage gain, output resistance, and overall gain. AV and GV, it is almost same it is. So the first, let us see the common source without source resistance RS. So here the input resistance R in, however for all it is very high, so ideally it is infinite. Okay, ideally it is infinite for all the amplifier types. Next is open circuit voltage gain. So for the common source open circuit voltage gain, we have calculated already, it is minus GM into RD. Actually this is minus GM RD parallel to small letter R0, but for the analysis purpose we'll be neglecting the small letter R0. So it is approximately equals to minus GM into RD. Next is output resistance. Output resistance is equals to RD. If R0 is included, small letter R0, that will be parallel to this one, RD. Next is overall voltage gain, AV or GV, which is nothing but minus GM RD parallel to RL. Means RL, load resistance, we need to include for the overall voltage gain. Okay, for the open circuit voltage gain, we need not bother about the load resistance, but for the overall voltage gain, we need to calculate the load resistance RL. Next is the common source with the RS. With the source resistance RS, so the input resistance will be infinite and the open circuit voltage is minus GM RD divided by 1 plus GM into RS. In the sense, when I compare common source without RS with RS, the gain will be reduced by the factor 1 plus GM into RS. Okay, and then output resistance remains the same, that is RD, and the overall voltage gain also it reduces. You compare these two equations, it differs by 1 over 1 plus GM into RS. So you can conclude that common source with RS, the overall voltage gain reduces by the factor 1 plus GM into RS, where GM is a transconductance, so it reduces by the factor 1 plus GM into RS. Okay, and this is also equals to, so you can rewrite this equation, that is excluding GM in the numerator. How we can write this is RD parallel to RL, taking GM to the denominator, so it will be 1 over GM plus RS. Okay, next is the last one, that is what we have discussed today, source follower or common drain. However, your input resistance, it will be very high, ideally it is infinite, and the open circuit voltage gain, it is 1. Okay, in output is equals to the input. So the overall not overall, output circuit voltage, open circuit voltage gain is 1, and then output resistance is 1 over GM, and then AV, overall voltage gain, will be RL divided by RL plus 1 plus G. So this is what the summary of your MOSFET amplifier. So that completes the various configurations of MOSFET amplifier. So today we have seen the last configuration, that is common source amplifier configuration. So we have discussed, so in your syllabus common gate amplifier configuration is not included. So we have discussed 3 configuration: common source without RS, common source with RS, and the source follower or common drain amplifier. Okay, thank you.